Okay, I want to make a couple of connections between arithmetic sequences and the way stuff works in nature. So first, let us review what an arithmetic sequence is in the first place. So it's simply a set of ordered numbers, numbers that are in a certain order. Uh, I'll just do a really super duper simple one. 3, 6, 9. Okay, it's a set of numbers. All right, there's numbers in there. It's a set because there's a well-defined rule that allows certain numbers to be in here. Um, and they're ordered numbers. They're put in order. You know, in this case, it's from to least to greatest, 3, 6, 9. In which the differences between the numbers is always the same. So the difference here, you know, going from 3 to 6 is 3. Going from 6 to 9 is another 3. So, you know, the next, I should say, this goes on forever. The next number here would be 12. The next after that would be 15. Or, you know, if I'm going this way, the next number would be 0, and then negative 3, negative 6. You know, you get the idea. So that's an arithmetic sequence. You know, just the difference between the terms or is always the same number. In this case, it's 3. You could have, it could be anything. All right, so we could actually describe an arithmetic sequence as a, we could do it as a linear function actually. Just kind of kick it up a notch. You can list them. You can list out all the numbers like this in set notation. But if you want to deal with, you know, if you don't want to write it all out, you could write it as a function, as an equation, which would allow you to calculate, you know, what's the thousandth term in this sequence, you know, something like that. So you don't have to actually physically write it all out. This equation sort of packs all that information you could have into something very compact and sleek. So what this is really saying is, the term that you want to find, you know, like the second term, third term, thousandth term, whatever, is the first term plus the number of term that you want. You know, so if you want, so the number of the term that you want minus 1 times whatever that difference is. In this case, it would be 3, the common difference. So let me, you know, to make it concrete here. So the term that you're looking at. So I want the third term in the sequence. That's equal to the first term. So in this case, 3 plus n minus 1. So I want the third term. That's n. So 3 minus 1 times the common difference, which is 3 in this case. Right? So if I actually do that out, 3 minus 1 is 2. 2 times 3 is 6, plus 3 is 9. So the third term is 9. Ding, 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 which we knew because we could just look at it. But so you can see now I could actually find what is a 70 billion, and I could just plug that number in and, you know, calculate it. Right? So it's very powerful. So I don't have to write everything out. So an arithmetic sequence can be written out like this, or it could be described as a linear equation like this. Yeah? Okay. With all that gigantic introduction out of the way, let's look at a couple examples of where this would be useful. So Halley's Comet last came close to the sun and became visible to the naked eye in 1986. All right. If its orbital period is 76 years, calculate the next 3 years the comet will appear. So we've got a situation where here's the sun, and then there's Halley's Comet. Let's say it's like that. Here's, I don't know, what am I drawing? Right? This comet takes a certain amount of years to do an orbit around the sun. It goes really far away, but then, you know, every 76 years it comes back again, Let's put the Earth. Let's put the Earth there. There's the Earth. So every so often the Earth gets to see Halley's Comet, right? And that orbital period is 76 years. So it does this every 76 years. Roughly. We're going to assume it's exactly 76 years. It's actually uh, not quite that precise because uh, the orbital period of the comet is influenced by the gravitational force of the planets going around. It might have some gravitational interaction with other um, asteroids. I don't know. It's not exactly that precise. But we're gonna pretend. And actually, just total side note here. I read an article that was arguing that a couple of astronomers calculated that Halley's Comet was going to collide with something, and then they actually observed some, brighter than usual um, radiation coming from the direction of Halley's Comet. So they hypothesized that actually Halley's Comet collided with something and is no more. So Halley's Comet might never come back, but maybe it will. All right. With all that out of the way, so we could think of this as an arithmetic sequence. So, the last time Halley's Comet came close to the Sun and we were able to see it was 1986. Okay? And then there's going to be, so its orbital period is 76 years. Calculate the next 3 years the comet will appear. So, there'll be 3 more years here. And what's the common difference? Common difference is the orbital period, So, we saw it in 1986. 76 years later, we're going to see it. 76 years after that, we're going to see it. 76 years after that, we're going to see it. Yeah? So, you could do that. So it's probably easier just to add 76 each time. I'm just going to use a calculator to do it quickly because I feel like I'm going over time with this lesson. So, 1986 plus 76. So 2062, if it did not blow up, we should see it roughly in 2062 plus 76 is 2138. We'll all be goners by then. Actually, I don't know. Maybe this lesson will be seen 100 years from now. Wouldn't that be great? And then plus 76. 2214. 2214. I feel like I should write a sci-fi novel called 2214. Anyway, those will be the next 3 years. There's a common difference of 76. So we could actually write an equation like A of n equals the first term, 1986. Is that the first time Halley's Comet was ever seen? No, it was seen, a couple thousand years ago, I think. But you can start a sequence anywhere. I mean, you could consider this to be the starting place. So the starting term plus n minus 1 times the common difference, which is 76 years. So this will tell you, so if you consider this the starting place, which we are, this will be the fourth term relative to that starting place. So, yeah. Okay, one more. The Earth has a circumference of about 40,000 kilometers. So, if we're looking down at the Earth and we look at this is the equator, we're looking at the North Pole here, or the South Pole, whichever, I don't know, you pick what direction you want to view this from. But the circumference, or the distance around the middle of the Earth, is 40,000 kilometers. Or 40,000 kilometers. Okay. Alright, so every day the Earth does a complete rotation. So, that's what makes the sun rise and set. Which means if you do nothing but stand in one spot on its surface, so here you are, standing on the surface of the Earth. If you do nothing but stand in one spot on its surface for a day, you will have done a 40,000 kilometer lap around the center of the Earth. So you go 40,000 kilometers, like that. What is the total distance of all your laps around the center of the Earth after a week? So every day you're doing a 40,000 kilometer lap. So I want to know, after 7 times around, how many kilometers have you done just by standing there? Kind of a weird problem. I was scraping the bottom of the barrel here to come up with some real world examples. Um, so our common difference, so we're adding 40,000 kilometers each time. So let's just write that. Um, what's our first term? Uh, 0. You haven't gone anywhere yet, so let's call it 0. So we'll just leave that. We won't. All right, no, fine. I'll put 0 in there. So first term is 0 plus n minus 1. And what's our common difference? Well, we're adding 40,000 every time, so 40,000 kilometers. Okay. So I'm going to do this with the equation because this for the Halley's Comet is easier just to kind of put them in by hand. Now I'm asking how many kilometers have we done in laps around the Earth after a week? So that's 7 terms. So we really don't want to do that by hand. So we want to find the 7th term, after a week. 7th term, yeah, after a week. So a of 7 is equal to 0 plus 7 minus 1. We want the 7th term, n times 40,000. So we've got 7 minus 1 is 6 times 40,000, which would be 240,000 kilometers. That's actually, I'm realizing that's assuming that the first day you don't go anywhere. So actually, this first term should have been 40,000. So add 40,000 to that. So that's how many kilometers you do in laps around the center of the Earth. Kind of an absurd example. And by the way, the center, the Earth is orbiting the sun, so it's doing millions of miles every year, and then the sun is orbiting the center of the galaxy, so it's doing billions and billions of miles, and etc. Anyway, all right, arithmetic sequences. Two approaches. Just fill out the terms by hand, or write an equation so you can figure out whatever term you want to figure out.